hell's going on here? Give me my diamonds!
Welcome back. So last week we talked about waves. We talked about how waves are repeated disturbance that transfers energy. So we had like our mass on the spring or the pendulum that's going between different types of energy and then back, and different types of energy and then back. And we said that there are really two main categories of waves: longitudinal waves and transverse waves. And so far, the only ones that we really covered are mechanical waves, or waves that require some kind of medium. And so sound obviously is a mechanical wave because it requires those air molecules to vibrate for sound to travel. If you were in deep space where all the molecules around you are so far spread apart, there wouldn't be any sound that can travel, and so you can't have transmission of that wave. There are some waves, though, that don't require a medium, specifically light. Light doesn't require a medium because it comes from the sun through space to us. And we know that light is a wave because it does all sorts of things that waves do, like specifically reflection and refraction, which we're going to talk about in this video. Reflection's an easy one to visualize. We've all seen it before. And so you could think of reflection as just a wave that comes out, hits some boundary, and then bounces back. So maybe it's a sound wave that leaves your mouth, vibrates the air molecules until it hits the wall, and then reflects back. Or maybe it's just the change between two medium. Maybe it's a light going from air to water, and as you get that boundary between air and water, light reflects back. And so if we want to simplify this to put some mathematics to it, maybe we won't look at the whole light, maybe we just look at a single beam or a single ray of it. And if that's the case, then reflection looks a little bit easier. You'd have some incident ray or some incoming ray that hits a surface and then reflects off. And you could measure from this dotted line to either the incident or reflected ray. You'd have angle in or angle out. And this dotted line, that's just our normal. That's a line that's perpendicular to our surface. And we can relate angle in and angle out with a very complicated formula called the law of reflection. And the law of reflection looks like this. Angle of incidence equals angle of reflection, or angle in equals angle out. And they just are the same. That's the whole idea of reflection. Incoming angle is the same as the outgoing angle. And you want to get into the habit of measuring from the ray to the normal. I agree that these complementary angles down the bottom are going to be the same as well. I think that's like alternate interior angles or something. But convention is from normal to the ray, first of all. And secondly, for our next law with refraction, it absolutely does matter that we measure from the normal to the ray. So even though these other angles are the same as well, it's a good idea to try to get yourself into the habit of measuring from ray to normal, just so that you don't mess yourself up for a refraction problem. Maybe you've seen this picture of refraction, maybe you haven't. If you were to put like a spoon in a glass of water, you get this picture where the spoon looks sort of like it's bent or broken off to one side, and the reason is because of this idea of refraction. So as waves are traveling through some medium, the density of that medium makes a difference. So for example, if we're talking about sound and you're in some material where the molecules are very closely packed together, it's real easy for the energy to travel from one to the next to the next to the next to the next. But if those molecules are farther spread out, like say in deep space, the energy can't really go from one set to the other, and so the wave isn't really going to propagate that well. And so depending on the density of your medium, that wave is going to travel at different speeds, and the speed of that wave is going to change how this thing actually looks to us. That change of speed as a wave enters a new medium is exactly what refraction is. All refraction is a wave changing its speed as it goes from one medium to the next. And if that speed changes by a lot, then there's a lot of refraction. And if that speed doesn't change by very much, there's not that much refraction. And there are cases where you could have absolutely no refraction that occurs as well, even though you go from one medium to a different one, as long as they have something in common, and that something is called the index of refraction. So how we measure how different those mediums are is with the index of refraction, which is this quantity right here, and all it is the speed of light divided by the velocity of light in that material. And so you can see, for example, if you had an n equals 1 value, that means that your velocity is the same as the speed of light. And because nothing can get above c, we should never have a fraction with a larger denominator, so we should never have anything that's less than 1. but the index of refraction will absolutely always be greater than 1. Looking at the formula n equals c over v, n is going to get bigger as v gets smaller. So light slows down as it enters into a material with a larger index of refraction. As n goes up, v has to go down. And the reason why is because of these pictures here, or at least a rough idea why. It's not really the best picture, but it's a good analogy. So you've got N1, which is the index of refraction on the left-hand side of this bold line, and N2 is the index of refraction on the right-hand side of this bold line. And you can see these wave fronts here that are traveling along the direction of this red arrow. And the right-hand side of the wavefront is going to get to this boundary first. And as they pass into that new material, they're going to become more compressed. And so those more compressed waves, they're going to be what causes this to turn towards the normal. As light enters into the new medium, it slows down, the wave bends towards the normal. Whereas if we go the other way, from a high index of refraction to a lower one, then we're going to bend away from the normal. So the way I always think of it is you bend up, and away from the normal as your speed increases. You speed up, you bend away from the normal. This simulation from PhET has a laser. It has air on the top and water on the bottom. And we can see that the index of refraction for water is 1.33, which is greater than the index of refraction for air, which is 1.0. So there should be some refraction that occurs. If we turn on this laser, we can see that there is an incident beam that comes in, a reflected beam with a lower intensity that goes out, and our refracted beam. And we can see that this is moved closer to the normal than its path if water wasn't there. So this has slowed down. It's moved closer to the normal and slowed down. And we know already that there's a way to relate the angle of incidence to the angle of reflection. And so there should be a way to relate the angle of incidence with the angle of refraction. And it is based off of one of the greatest names in physics, Willebrord Snellius. And the formula that we're talking about is Snell's Law. And so here it is, Snell's Law. N1 sine theta 1 equals N2 sine theta 2, where N1 and N2, those are just the indexes of refraction for one side of the boundary and the other side, and then similarly, theta 1 and theta 2 is the angle on one side and the angle on the other. And this formula only works if you're measuring from the normal. So you have to make sure that you're going from that line that's perpendicular to your surface to either the incident ray or the refracted ray. Let's give this formula a try. Let's see if we can figure out what angle our refracted ray will actually be inside of water if it comes from air at an angle of 30 degrees. So let's give that a try.
The moment's handy for a piece of candy. Just name your brand, they're all so grand. Hey, what do you think of a nice cool drink?
All we're trying to do is use Snell's Law to figure out the angle inside that water. And so I filled in a table here with the information that we know. We know the index of refraction for air is 1, and that's just always going to be true. We know that the incident angle is given to us as 30 degrees. And we also know that the index of refraction for water is 1.33. We saw that in the simulation before, but it's something that you can easily look up as well. So if we want to find out the angle inside that water, we have to use Snell's Law. N1 sine theta 1 equals N2 sine theta 2. And it's okay to use degrees in this formula as long as you want degrees on the other end, but if you're looking for radians, you should plug in radians. You want units to be the same on either side of the equality. So what I'm going to do to find theta 2 is I'm first of all going to calculate what N1 times sine theta 1 is. And I'm going to have to work in radians just because Excel does, but that's perfectly fine for you with your calculator. There's no reason why you couldn't just plug in degrees. So this is what I'm getting on this side. And now to get theta 2, I'm going to do the inverse sine of this value divided by N2. So it is just going to be 0.5 divided by N2. And then in here, we want to get the inverse sine of that. You gotta spell degrees right for this to work. So the degrees of arcsine, what we find is 22 degrees is the angle that we would expect. So if we jump back over to our simulation for 22 degrees and change this to water, there we are, just past 20. So 5, 10, 15, 20, and there is the angle of refraction that we're making. Okay, now it's your turn to give one a try. Let's say that this time we're going to have an incident ray that's at 50 degrees, but this time we're going to start in water and go to air. Find out what that angle of refraction would be in air if we start from water. Give this a try, and then I'll show you what I got.
So come on, folks, let's join the band as we all head for the refreshment stand.
All I have to do for my table is just change around these starting values to get this new answer. So we start in water, so this will become 1.33. And we can see that if the medium doesn't change, the angle doesn't change. We're starting at 50, and we're going to air. And we can see that Excel doesn't like this. It gives us a bunch of these pound signs right here. And so that means that there must be something screwy going on with that angle. Your calculator may have given it to you as undefined. So if we jump back over to this demo, let's see what that physically would look like. So we start at water, and what you see is that we don't have any refraction on the other side. We only have reflection. And so if we sweep this angle for a little bit, we can see here at an angle less, we have refraction, but if we go lower than that, we don't. Lower than that, we have all reflection. So this is what's known as total internal reflection. There are combinations of angles and indices of refraction where at that combination, you can only have reflection. And this is how materials like fiber optic cables and waveguides work. They work off of this idea that there are certain combinations that make Snell's law blow up, and that's because they won't refract at all. There will only be reflection. That very quickly is a story on reflection and refraction. You've got reflection where a wave hits a boundary and bounces back, and you've got refraction where a wave gets to a boundary and then passes through, and as it does, its speed changes. It either moves towards or away from that normal line. And it's all based off of this idea of the index of refraction, which determines how much that wave either speeds up or slows down. And there are certain combinations where that division in Snell's law gives you something that the sine function doesn't like and cause it to blow up. And in that case, you don't have any refraction at all. You have only total internal reflection. And that's about it for all this wave stuff that we need to talk about. It is the bare minimum of this topic, and there's far more that you could cover with this. You could do an entire year's worth of content and beyond on just waves, but this is the fundamentals that we need, especially with this weird no regions situation that we've got going on. So this is as far as you really need to go. After this, I recommend the video on the history of light, and then we can move on to the photon and all sorts of cool quantum mechanics stuff. And so that's where we're headed next. Check out those videos, and I'll see you next time.